The next thing we need to look at is something called inverse functions. A lot of people think of inverses meaning opposite of, and that's not an entirely bad way to look at it, but that's not always the best way, not a perfect way to look at it. Now let's just start off with a table of values. Let's say that there's some function f of x such that you put in an x and you get out the y, and some of the inputs and outputs maybe would look like this. 1, 3, 2, 6, 3, 9, 4, 12, and 5, 15. Now, what an inverse function would do, and they are denoted using a notation that looks like f to the negative 1 power, but it doesn't actually mean negative 1 power, it does mean inverse. But with an inverse function, the way its x's and y's would work is that its first x would be 3, its first y would be 1, its next x would be a 6, its next y would be a 2, and followed by 9, a 3, a 12, and a 4, and a 15, and a 5. In other words, this inverse function is taking the original outputs from the first function, putting them in, and giving back the original inputs. So in that sense, it kind of is the opposite. So one of the things you'll be asked to do is to take ordered pairs, and from those ordered pairs that represent a function, create an inverse function. So if we had a 1, 1, a 2, 4, a 3, 9, a 4, 16, if that constituted your original function, then the inverse could be found just by switching the order. 1, 1 would stay 1, 1 because it's two numbers that are the same. And we'd have the 4, 2. We'd have a 9, 3. And we would have a 16, 4. And that would be your inverse function. Now, with ordered pairs, an inverse function is easy to find. Another place that it's easy to find is, or at least easy to inspect, is graphically. What a function looks like when you look at a function versus its inverse is there's sort of a magic line that defines what you're going to see. An inverse function will be the mirror image of the original function when you look at it across that line. So, on the graphing calculator, let's look at y equal to, our first function will be x to the power 3. And if you think about what should be the opposite of x cubed. Now if you think really hard about that, you might figure out that the opposite of x cubed should be cube root of x. Some of these inverses, they just make sense. So when we graph both of these, what we're going to see, and actually that might not be the best view, let's go with a zoom standard, but there's the original x cubed being drawn, and there goes the cube root of x. Now you should hopefully you can see that those are in fact mirror images of each other across the line y equals x. As a matter of fact, it's often helpful to come back and put in y equal x and graph it again with that line in there so that it's more clear that the x cubed graph, which is here, is the inverse of the cube root graph, which is there. So that's what they look like graphically. Now the problem with this is, with these particular types of functions, is that not every function has an inverse function. Alright? For example, If you look at the function f of x equals x squared, and you look at some x's and some y's, for x squared you can put in a 1 and you'll get out 1. Put in a 2, you'll get out 4. But if you put in negative 1, you also get out 1. Put in negative 2, you also get out 4. The reason for that, clear off some of these other graphs, is that the graph of x squared is symmetric about the y-axis. That's because x squared is an even function. So what happens when we try and look for our f inverse, whatever that might be, and a lot of people would naturally assume that f inverse for x squared is square root of x. But if we take this original output, put it in, we get out the 1. Take the 4, put it in, we get out the 2. But the problem is when we put in this 1, we get out a negative 1. When we put in this 4, we get out a negative 2. As you know, the definition of function says every input has to have a unique output. But here we've got two different outputs. So x squared by itself, as it is right there, doesn't have an inverse. And the main reason is that x squared fails something we call the horizontal line test. The vertical line test tells you whether you've got a function or not. The horizontal line test tells you whether that function has an inverse or not. And since I can hit this parabola with a horizontal line more than once, it doesn't have an inverse. So what we can actually do is come in here and say, if we let f of x equal x squared with x greater than or equal to 0, then we've eliminated this possibility, we've eliminated that possibility, therefore this isn't going to happen, that's not going to happen, and with the correct restrictions, our graph will have an inverse. Now, to find this inverse algebraically, you got to remember what's happening. From the original function to its inverse, x's are trading places with y's, y's are trading places with x's. So, algebraically, that's exactly what we will do. We will exchange y for x and x for y to find an inverse. So let's say our original function was f of x equaling 2x plus 1. Of course, we need to write this as y equal 2x plus 1 because we need to work with our x's and y's. And again, remember, when you go from a function to its inverse, x and y trade places. So this will become x equaling 2y plus 1. So the x's and y's have traded places. Now I solve for the new y. Subtract 1. I get that 2y equals x minus 1. Divide by 2. Divide by 2. And y would equal the x minus 1 over 2, which means that from this original f, our f inverse of x is the x minus 1 over 2. It's the y you solve for when the x and y trade places. So let's say we had f of x equaling the fourth root of x. Now, of course, we have some restrictions we have to pay attention to. Since this is an even root, we have to say x greater than or equal to 0. And since also it's an even root, we have to say y greater than or equal to 0. Because what's going to happen is the original restrictions on x are going to become the new restrictions on y. The original restrictions on y become new restrictions on x. So we've got that y equals the fourth root of x, raising both sides to the fourth power. I get y to the fourth equaling x. Now remember, x and y have to trade places, so this becomes x to the fourth equaling y. So your f inverse of x is x to the 4th power. Again, with the restrictions, x greater than or equal to 0, and with the restriction y greater than or equal to 0, to keep these functions true inverses of each other. Now, oddly enough, some functions are their own inverse. For example, if I have y equaling 1 over x, I have to make the statement x can't be 0 for obvious reasons. Trade places, and I get x equaling 1 over y. Alright, multiply both sides by y to clear the fraction, and you get y times x equaling 1. Divide off the x, get that y equals 1 over x. So the f inverse function is 1 over x, and same restriction, can't have x equal to 0.